Have you ever thought about how something that's supposed to be incredibly strong, like a giant steel beam, can just, well, break? I'm not talking about from some huge, obvious impact. I mean, seemingly out of nowhere, after years and years of doing its job perfectly. It's a total paradox, right? It's something that has challenged engineers forever. And the answer? Well, it's hidden deep, deep inside the metal itself. So take a look at this. It's a summer evening, 2007 in Minneapolis. This is what happened. A massive steel bridge packed with rush hour traffic just collapsed straight into the Mississippi River. And the scary part? There was no earthquake, no explosion, nothing. 1 second, it was standing strong, and the next, it was just gone. So that just brings up the big question, right? How in the world is that even possible? How can solid steel, something we designed to hold thousands of tons, just shatter without any warning? Well, the answer is a kind of hidden enemy, one that works right out in the open. Okay, so to really get this, we've got to throw out a common idea about strength. See, we all kind of think that to break something really, really strong, you need one single massive force to do it. But it turns out that's really only half the story. So on one hand, you've got what we'll call static failure. This is what we all picture, right? A single, huge force that's just too much for the material. It's like pulling on a rope so hard it finally snaps. But then there's the other side, fatigue failure. And this one is way sneakier. It's basically death by 1,000 cuts. Or, to be more accurate, it's death by millions of tiny pushes and pulls. And here's the kicker. Not a single one of them is strong enough to cause any damage on its own. And that's what makes it so dang terrifying. There's this great quote from a materials science textbook that calls it catastrophic and insidious, and that's the perfect way to put it. It doesn't warn you. You don't get any groaning metal or bending to give you a heads up. Nope, it just happens suddenly. All right, so this silent killer has a name, fatigue. And the way it does its damage is through something called cyclic loading. So let's unpack what that actually means. So here's the textbook definition. Fatigue is basically the tendency of a material to break when you apply stress to it over and over and over again, in cycles. But here is the absolutely critical part. These stresses are way, way below the level that would break the material if you just did it once. That's the whole key right there. A really simple way to picture this is a rotating axle. Just imagine one single tiny spot on the surface of that axle. Every time it rotates, when that spot gets to the top, it gets squeezed. That's compression. And when it swings around to the bottom, it gets stretched. That's tension. So with every single turn, it's squeeze, stretch, over and over. And every single one of those rotations, doesn't matter if it's a car axle, an airplane wing flexing up and down, or even a bridge just vibrating as cars drive over it, every one adds one more cycle of stress. It's this relentless, non-stop push and pull on the very structure of the metal. So how does that relentless push and pull actually lead to a catastrophe? Well, it all starts with a flaw so tiny you can't even see it. And it just builds from there, one cycle at a time until everything comes apart. It pretty much happens in 3 steps. First, you get initiation. This is where a tiny, invisible microcrack is born. Then comes propagation. With every single push and pull, that little crack grows just a tiny, tiny bit. And this can go on for millions, even billions of cycles. And finally, fracture. The crack gets so big that what's left of the metal just can't take the load anymore, and that's when it fails. Boom. Suddenly and completely. And what you're looking at here, this is the result of that second stage, propagation. This crack wasn't made in an instant. Nope. It grew, little by little, cycle after cycle, totally hidden deep inside this metal part, just waiting. So where do these killer cracks even begin? Well, the scary answer is pretty much anywhere. We're talking about microscopic surface scratches, sharp corners in a design, little dents or tool marks left over from when the part was made, even the threads on a simple bolt. Literally any tiny imperfection can become what we call a stress concentrator, basically the perfect starting line for a fatigue crack. Okay, so this all leads to a really important question, kind of a human side of it all. If we know this happens, why on earth are fatigue failures still so common? Why is this such a huge, persistent blind spot for so many designers and engineers? I mean, the scale of this problem is it's staggering. According to the experts, the people who write the textbooks, Fatigue isn't just a cause of failure in metals, it is, by far, the single biggest cause. 90%. Just let that sink in for a second. 90. That means that for pretty much every 10 metal parts that fail, 9 of them failed because of fatigue. It's almost always the culprit. So why the blind spot? Well, honestly, it comes down to complexity. It's one thing for an engineer to calculate, can this beam hold 10 tons right now? That's relatively straightforward. But it is a whole other level of complicated to try and predict how that same beam will hold up after, say, 50 years of millions of vibrations and constant temperature swings. It's just incredibly tough. And sometimes the starting point is something so small you'd never, ever guess. There's a famous case of an aircraft failure that was traced all the way back to an inspector's stamp. Just a little mark to say it passed inspection, but the person who stamped it hit the hammer just a little too hard. That tiny dent, that became the birthplace of a fatal fatigue crack. But there is good news here. Engineers aren't helpless. They've actually come up with some really powerful ways to fight back against this invisible enemy. And the whole game is about designing things with fatigue in mind, right from the very start. It really all boils down to a few key ideas. For starters, you eliminate sharp corners. You want everything smooth and rounded. You also want surfaces to be as polished and perfect as you can get them. You have to avoid any scratches or little marks when you're making the part. And then there are even clever tricks like something called shot peening. It's kind of like blasting the surface with millions of tiny metal balls, which creates this protective skin that literally squeezes the surface together and stops cracks before they can even start. So when you boil it all down, the big takeaway is this. In engineering, especially when you're building stuff that has to last for millions and millions of cycles, the small details aren't just details. They are everything. That tiny scratch, that sharp corner, that little stamp mark, those aren't minor flaws. They are potential disasters just waiting for their moment. And that really leaves us with one last thing to think about. This whole phenomenon of metal fatigue. It's such a powerful reminder that the most dangerous threats are often the ones you can't even see. And it just makes you wonder, doesn't it? What other invisible threats, what other silent killers are we overlooking in the incredible, complex world we're all building?